Welcome back everybody. Okay, so in the next two videos, let's see two applications of the axiom of choice. The first one is an application using Zorn's lemma, and the idea for this one is to prove a very basic theorem of algebra, I guess of all of math actually, that every vector space has a basis. Okay, so please, if you don't remember what this is, stop the video, go back to your notes from algebra to review what this is, because we'll use vector spaces in this one. So let's start considering a vector space. So let's V be a, let's call it K vector space, where K is a field. Right? For every field, we can have a vector space over that field. And let's just recall what the basis was. A subset B of V is a basis if it is linearly independent and the span of B is the whole thing. The span is everything you can get by a linear combination of elements of B. Okay, so a basis was that. It's linearly independent and every element of the whole space can be written as a linear combination of elements in the base B. So a basis is a class of set of vectors, and another characterization of basis is that every element of the whole vector space V can be written in a unique way as a linear combination of vectors in the basis, and that's because of the linear independence. You get a uniqueness from the linear independence, and that's why they are so important, because they give you a representation of each vector in terms of the ones in this basis in a unique way. So how is that you use Zorn's lemma to get such a basis? Well, we have to start defining what's our collection of sets. So we start by taking all the sets of vectors such that which are linearly independent. Okay? So now we need to show, if you want to use Zorn's lemma, that the union of every chain is belongs to the set. So we claim that the union belongs to A, so that the union of this chain is linearly independent. So how do we show that? Well, let's prove linear independence. So consider vectors v1, vl that belong to the union, and elements and scalars k1, kl that belong to the field, such that the sum of ki times vi, I equals 1 to l, equals the zero vector, right? If you want to show that a set is linearly independent, you have to consider a linear combination of the vectors and show that that all the coefficients are zero, right? That's how you prove linear independence. Okay, so these vectors belong to the union, right? So each vi belongs to some bi that belongs to B, right? Because if you belong to the union, you must belong to one of its members. Now, there are only L of these sets, and they're all nested because they copy this collection B is a chain of linear independent sets. So if you have a chain, any two elements are, well, one a subset of the other, so it's the largest one. So let B be the largest of the B's of I's for I between 1 and L, right? So they are all nested. It's the largest one, and that one belongs to I, and I is linear independent, and V1, VL, they all belong to I. So that means that from here we get that all the KI's have to be zero because they belong to this linear independent set I. Okay, so essentially what's going on here is, which happens in a lot of cases when you apply Zorn's lemma. So the property of linear independence is a property about finite subsets, right? So it's a property about finite tuple of vectors, v1 up to vl. So for all finite tuples of vectors, v1 up to vl, every linear combination satisfies, well, is non-trivial. So what you get is that when you're applying something up to the union of this chain, but since what you care is about finite tuples of vectors, the finite tuples must belong to elements of the chain, and they have a maximum because they are all nested, so they all belong to one single element in the chain. And then, since that element is linear independent, then the property you want, these vectors satisfy the property you want, right? So this is very common. And so here we have that, yeah, the whole union has to be linear independent, and therefore we can apply Zorn's lemma. There is a maximal, by Zorn's lemma, there is a maximal linearly independent subset of our vector space as a maximal element of this set calligraphic A of linearly independent subsets. And now we claim that B is a basis. Actually, if you remember your linear algebra, another characterization of being a basis is to be a maximal linear independent set. So we have it right here. The reason why it's that is because if B wasn't a basis, so if the span of B was not everything, then you can add something to B and you will have a bigger element. So otherwise, if the span of B wasn't the whole thing and we could choose a vector from it, we will have that B union this element would also be linear independent. So you could add a new element and have a larger linear independent set contradicting the maximality of B. Right, so it couldn't be that it doesn't span the whole thing, because otherwise you can have a bigger basis. So the fact that it's maximal implies that it spans the whole vector space, and that's how you get the basis. Okay, so this theorem is actually equivalent to the axiom of choice. So we can add this one actually to number 7, to another equivalent. And it's definitely an important statement in linear algebra, no? That every vector space has a basis. So here we're going to use a corollary of this result in our next right here. So the corollary is that there exists an isomorphism between R viewed as a group with 0 and plus, and R squared viewed as a group when you add with addition of vectors, where plus is addition of vectors. So if you have this vector and this vector and you want to add them, you're going to get the addition of the vectors, which is somewhere there. Yeah, so R squared is also a group if you adding vectors. As groups, they look very different, right? One is just the real, one is flat, it's one unidimensional. The other one is a bidimensional group of vectors. It's a group, right? You have the inverse vectors and stuff. And the corollary of the theorem is that they are isomorphic. So the corollary claims that it's a bijection between R and R squared, which maps 0 to 0. That's what it means to be isomorphism of groups. And also, if you have two elements of R and you add them together and then apply F, it's the same thing as first mapping them to the other side and get the corresponding vectors and then add those. Yeah, so those two things is what it means to be an isomorphism of groups. How do we get these? Well, the trick is to view R and R squared as Q vector spaces. Q is a field, yeah, and R and R squared are both Q vector spaces, right? You can multiply by elements of Q in the obvious way, and addition is the one that just mentioned right there. So with that addition and scalar multiplication by elements of Q in an obvious way, you can view them all as vector spaces, and they have the same dimension. What does it mean to be the same dimension? Well, to have a dimension means the size of the basis, right? So they both have infinite dimension over Q because there is no finite basis over Q that is going to give you R or R squared. But to have dimension in the infinite case, you need to have basis. So the previous theorem is the one that tells us that every two vector spaces have a basis. And then that's why we can say the same dimension. So we can consider a basis for these two guys and over Q, right? So these are as vector spaces over Q. And now is a claim that we're not going to prove today, which is that the cardinality of the base 1 is equal to the cardinality of the reals, and is equal to the cardinality of the base 2. Right, so we know that R and R squared, we're going to prove that R and R squared have the same cardinality. Actually, we proved that last time. But we're claiming that the bases have the same cardinality. And I guess the lemma that you need to prove here is that if your field is countable and your basis is infinite, then the cardinality of the span of this basis is equal to the cardinality of the basis. So when you do a span of an infinite set over a countable field, it doesn't increase the cardinality of the basis. So that lemma we might prove next week. So we don't have the tools yet. But okay, you can kind of believe that the basis that we need for R and R squared as vector spaces over the rationals have to have the continuum size. So once they have the same size, we take bijection f from B1 to B2, any bijection, they are equinumerous, so we can take a bijection, and then extend by linearity to an isomorphism from R to R squared. Yeah, remember that whenever since every vector in R is a linear combination over Q of the elements of B1, you map the elements of B1 through the bijection, and then you use the same linear combination on the other side, on the square side, and since they're both bases, you're gonna get an isomorphism. And this isomorphism of vector spaces, the vector space contains zero, contains plans, and contains scalar multiplication. So in particular, it's an isomorphism of groups. So in particular, you have that it satisfies that. Actually, it satisfies more than that. It even preserves multiplication by rationals, the embedding that we get from here to here, which actually follows from this part up here. So yeah, these two guys, even though they look quite different, are isomorphic as groups. And actually, we're gonna mention later that it actually requires the axiom of choice to show that these two guys are isomorphic as groups. So you couldn't actually find an isomorphism. You couldn't build an isomorphism constructively. So there couldn't be a construction which doesn't use the axiom of choice for that isomorphism. So somewhat in the middle, you have to use the magic of the axiom of choice to say, oh, choose this and this and this, do this infinitely many, continue many choices to get this basis and the isomorphism. But there is no actually way of describing any of the isomorphism between these two guys. See you in the next video.